Hey guys, welcome to this video. So this one focuses on one of my favorite mega functions, well, probably my second favorite mega function, the NCO, Numerically Controlled Oscillator. If you don't already know, mega functions are important tools in the armory of an FPGA digital designer, and the NCO is possibly the most widely used in communication systems, waveform generation, and for good reason. These allow you to generate sinusoidal waveforms at a frequency chosen by the designer. But there's much more to NCOs than just signal generation. And in this video, we're going to look at how an NCO works, how we can design an NCO for a particular output frequency, and then how we can implement this NCO in Quartus and view the waveform coming out of the DAC using the picoscope. Hopefully by the end, you should be able to turn your FPGA into a signal generator. Let's get started. The architecture of the NCO is remarkably simple. You have a phase increment value, which is the input to the NCO, and you have an accumulator which uses the phase increment value and it just adds it to itself on each clock cycle. So you end up with a kind of sawtooth waveform. The waveform generation unit turns this sawtooth waveform into a sinusoidal wave. So the phase increment value actually sets the steepness of the sawtooth waveform, which consequently sets the output frequency of the sinusoidal wave. So really, the frequency is being set by the phase increment value. Now in hardware, it's fairly trivial to build an accumulator, but the real challenge in hardware is how do you do the waveform generation unit? One option is to use a lookup table. So this takes the phase and then you store in memory the associated amplitude corresponding to that phase. Now this is a convenient way of doing it, but it does have the disadvantage of requiring lots and lots of memory. So if your FPGA is short of memory, you might want to look at another option. Now another viable option is to use the Quartus algorithm. This method calculates the amplitude from the phase on a case-by-case basis. And the Quartus algorithm is quite good because it is a really efficient way of doing this. Now, the disadvantage with this method is you require logic, not memory. You require logic this time. So when you decide which one to use, think about the balance of resources you have on your particular FPGA. So we know that the phase increment value determines the increase in value of this sawtooth waveform on each clock cycle. And when the phase increment reaches its maximum value, it rolls back to zero. So this will continuously produce a sinusoidal waveform. And if you think about it, the frequency is determined by the step size, by this phase increment value. So if you have a higher phase increment value, your frequency will be higher because the period of the sawtooth waveform is smaller. Now, the total period of one generation of the sawtooth wave, and therefore one generation of the sinusoidal output wave, will be the number of steps multiplied by the clock period. And of course, the number of steps will be 2 to the power of m, where m is the bit width of the accumulator value divided by the phase increment value. And once we have this, we can just do 1 divided by the period to get the frequency of the output clock. Now let's do a real example. Now, if we consider the accumulator bit width to be 32 bits, and the phase increment value is the number shown on the screen here, and we consider the clock, this is the square clock being fed into the NCO, to be 100 megahertz, then we can just apply this formula to get the output clock frequency. In this case, we should get an output clock of 1 megahertz. Now you can use this formula to calculate the phase increment value required to get any output clock frequency. So NCOs are really easy to use. Right, I think we're ready now to go over to Quartus and let's implement this numerically controlled oscillator. So I'm using Quartus Prime version 19.1. My design strategy here is to create a block diagram schematic file, new block diagram schematic file, and then I'm going to create my NCO. So I'm going over to the IP catalog, DSP, signal generation, NCO, and this will open the IP parameter editor. I'm going to use the same parameters as we discussed earlier on in this video. So I'm going to assume a 100 megahertz clock, and I want a 1 megahertz output frequency. So I'm going to name my NCO test. It doesn't really matter, and I'm going to go for a Cordic based algorithm to make my NCO. And in frequency, I'm going to use the same parameters we discussed earlier on in this video. So a 32-bit phase accumulator precision, angular resolution of 16 bits. We didn't discuss that previously, but I'll leave it at 16 bits. And a magnitude resolution, I'm going to go for 14 bits, okay? This means how many bits does the output signal have? And the reason I'm choosing 14 bits is because that matches my digital to analog converter. So everything else is exactly as we discussed previously. And the parameter editor has already worked out the phase increment value that we need to get 1 megahertz from a 100 megahertz clock. So I'm just going to copy this number because we do have to input that number into the NCO after it's been instantiated in our design. So just because it says 1 megahertz here, that does not mean the NCO will be generated for 1 megahertz. It just means this is the phase increment value you would need to put into it to give you 1 megahertz. So this is just a suggestion, and I'm going to copy that and we'll use that later. So I'm going to hit generate HDL. Simulation, I don't plan to simulate, but let's generate the simulation model anyway. And I'm going to hit generate. So this should take a few moments, and so I'll hit finish, close. We get a pop-up message now telling us that we need to put the .quip file into the project. So I'm going to do that now. So I'm going to go to project, add, remove files in the project. And I'm going to look for the .quip file that was just generated by the IP parameter editor. So that should be in the project now. Oops, that's a previous project. So if I go to files, you'll see the .quip file in our project. Now, where do we go next? I've got the NCO generated, but we now have to find a way to instantiate this in our project. And we also have to find a way to generate the 100 megahertz clock. Now, the Cyclone V starter kit, it only has a 50 megahertz input clock. So we're going to need to generate a phase locked loop. So I'm going to just instantiate, or first of all, generate a phase locked loop to multiply the input clock by 2 and give us the 100 megahertz clock to feed into our NCO. So very straightforward. The reference clock is 50 megahertz and the desired clock frequency is 100, which it already is. We don't need a locked output port, and I'm going to hit finish. So that should be generated now. So I'm going to put that into my BDF. Generation successful, so I'll hit exit. And this time it automatically puts the .quip file into the project. So I'll just hit yes. And now we can see the phase locked loop .quip file. That's the synthesis file in our project. So I'm going to double click and I'm going to hit project. And I'm going to put the phase lock loop into the project. And I'm going to have an input pin into the reference clock. And this input pin will come from the 50 megahertz oscillator on the Cyclone V starter kit. So I'll have to go to the Cyclone V starter kit user manual to find out which pin assignment we need to bring in that clock. Now, for the numerically controlled oscillator, we have our numerically controlled oscillator mega function, which has been generated. Now, what I'm going to do next is I'm going to create a Verilog module, and I'm going to use this as a wrapper. So it's just going to be a module to instantiate the NCO within, and also to provide the signals needed by the NCO, for example, the phase increment value, and just route the clock into the NCO. So I've got some code from a previous project here just to save time. Just need to check the name is matching. So this one should be NCO test. Yep. So this is the module name, and this is the instantiation name. This second one can be wherever we want, but this first one has to match the generated mega function within the project. Now, I've already got here the phase increment value that should give us 1 megahertz on the output. So that should be okay. So once that's done, just going to save the name of the module, then save the .v file. That .v file should appear within the project navigator. I'm going to right click and I'm going to create symbol files for current file. So save the block as block. This should generate a block from the NCO wrapper module. So if I double click, we should see the NCO wrapper module here. So I'm going to put that in and then route the 100 megahertz clock into the NCO wrapper. The only thing we need to do now is just make sure the reset pin is wired to a 1. So we can go into the primitives. We can go to other and get VCC. And we can route this into the reset pin. Right, okay, so I'm going to now make the block the top level entity, and we can do analysis and elaboration. Now, at the moment, I haven't routed these NCO the NCO output signal to my DAC. Okay, so in a minute, I'm going to create another module here with the appropriate interface code for my 14-bit digital to analog converter. And then I'm going to route those pins to the 14 pins of the DAC. Before I do that, I'm going to test this design using signal tap. Okay, so if we configure signal tap properly, we should be able to see the sinusoidal waveform on these pins. So analysis and elaboration is successful. So the clock, the 50 megahertz clock is pin H12. So I'm going to go back to my design. I'm going to go to assignments, pin planner, and I didn't name that clock. I should have named this clock instead of pin name 1. That's bad practice. Anyway, I'm going to make the pin assignment H12. I'm going to go file, close, and now we can do compilation. Now, I said I was going to use signal tap to inspect the design initially. And the good thing about signal tap is you don't need to have any output pins. You can actually inspect the signal inside the FPGA. So you don't need any logic outward facing. That's one of the good things about signal tap. So that's exactly what I'm going to do here. And it's a good thing to do because you can have confidence that your design is working before you progress the design further to the next stage. So let's do compilation. Okay, so that's compiled. So now I'm going to go to signal tap. So I'm going to go to Tools, Signal Tap, Logic Analyzer. We have to, unfortunately, compile again because you have to compile once for signal tap to be able to find the signals that you want to observe inside your FPGA. So to find those signals, I'm going to double click in this space here. And I'm going to use signal tap pre-synthesis because as it stands, our design will probably be synthesized away during the compilation process because there's no real place for the signals to go. So the compiler is kind of ruthless in trimming away any logic that doesn't have a logical kind of output. But if we select signal tap pre-synthesis, it will show you the signals before that process has taken place, and we can pick them off, put them in signal tap, and then they will be preserved. So let's select that and then hit list. The one I'm most interested in seeing is the output from the NCO. And of course, that will be out sine. So I'm just going to put that one in, insert, and it's there. So as I said before, we do have to compile again. The other thing Signal Tap needs is a clock. So I'm going to click inside there. Again, Signal Tap pre-synthesis, list the signals that it can find, and I'm going to tap off the phase lock loop output clock as our clock in this design. So that's okay. Now, the other thing we take note of here is the sample depth of Signal Tap. At the moment, it's going to give us 128 samples. I would like a bit more than that. I'm going to go to 1K. Now, of course, the trade-off here is this will eat up memory on your device. So 1K should be doable for the FPGA we have here. So that's set up nicely. Next thing we do is recompile. So we're almost at the end of the compilation process here, and I just wanted to show you the logic utilization of this design. You can see it's changed drastically since we introduced the Signal Tap logic. Now, Signal Tap, the way it works is it builds kind of a logic analyzer inside the FPGA, and that allows you to see those signals in real time. And you can see now we have many more, much more memory utilization in the device and also more registers. So you always have to bear this in mind when you use Signal Tap. There's going to be an increased overhead of logic utilization because you have Signal Tap. I guess when you're happy with the design, you can take the Signal Tap part of the design out of it. But for the debugging stage, Signal Tap is an incredibly powerful tool, as we'll see. So the compilation process has completed successfully. So let's go back. And my apologies, I made a mistake earlier on. The phase lock loop is an active high reset, so this should be ground and not VCC. So I fixed this and recompiled, and we'll have a look at Signal Tap with the updated design. Okay, so here we go. I've programmed the device. This one has got the ground going to the reset pin of the phase locked loop, and we can hit auto run analysis, and as you can see, we have our 14-bit sine wave, and we could measure this, but I'm pretty certain this is 1 megahertz. We will measure it once we get this out of our DAC, but you can see the power of using Signal Tap in this case, because now I've got confidence that that signal is what it should be. Right, okay, so back to Quartus. Now we can be confident that the signal here is the 1 megahertz sine wave. So what we would like to do now is output this signal through my digital to analog converter. And I'm lucky enough here to have the THDB ADA daughter board on my Cyclone V starter kit, and this has a 125 megasamples per second 14-bit digital to analog converter. So this is absolutely ideal for this kind of signal. So what I'm going to do now is I'm going to write some interface code for this 14-bit DAC. And in fact, just to save time again, I'm going to copy and paste some existing code from another project. And this one actually is interface code for both the 14-bit DAC and the 14-bit A to D converter. I'm not sure if we're going to use the A to D converter in this video, but certainly we will be using the DAC. And you can see here I'm targeting channel B because this is a dual channel digital to analog converter. It's got channel A and channel B. For this one, we're going to output 14 bits on this output port here. Those 14 bits have to go to 14 pins, and those pins need to be chosen so they target the right pins on the connector, so they ultimately go to the digital to analog converter. So that's going to happen there. There's also a couple of control signals for the DAC. So DAC write B and DAC clock Both of those will be derived from the 100 megahertz clock, which already exists within our project. I'm going to save this module as out module, make sure it's in the main project folder, and then I'm going to create a symbol file for current file. We need to close or at least stop signal tap. It's still going. So let's create symbol file for current file so we can put the block here. Okay, so double click and our block should be ready and waiting. So there we go. So let's put that there. Of course, we need the clock to be coming from the 100 megahertz clock from the PLL. Signal in, that's going to be coming from the NCO, and DAC B, that needs to be the 14 pins to the DAC. Now, again, just to save time, I'm going to take this from an existing project. So I'll be back in a second with the right pins. Right, so as you can see, I've populated this design with some output pins going to the DAC chip. To update the pin planner, I need to do analysis and elaboration. Okay, so analysis and elaboration is successful. So I'm going to go to the pin planner, and what we should see is the pins appear, but they need to be populated. Again, to save time, I'm going to go to an old project and I can guarantee that these pins are correct. So just to save a bit of time, I'm going to copy and paste the DAC pins from this project into the new project. So it's a simple matter of pasting these in. I'm pretty sure those are correct. So now I'm going to close the pin planner and hopefully we should see our pins. So there we go. We can see the pin assignments. So what we need to do now is compile. So I've got my hardware ready. So I've got the Cyclone V starter kit here with the THDB ADA daughter board. This has a 14-bit DAC and I'm using a picoscope to visualize the output waveform from the DAC. So I've programmed the device and I'm looking at my picoscope, and as you can see, we certainly have a sinusoidal wave. So that's exactly what we expect to see. Now I'm going to add a measurement here so we can measure the frequency of this waveform. So let's just find the frequency measurement. So it's fairly small, but you can see the frequency is 1 megahertz. Now, I don't think this is accurate enough to measure very, very small shifts in frequency. So this would not be able to measure the frequency resolution of this NCO, but we can certainly see that this is giving us a 1 megahertz output frequency. So I'm going to go to spectrum mode. This will give us a frequency domain view of the signal. So at the moment we've got a sampling rate of 10 megahertz, and so there we can see 1 megahertz. We've got the spike. We've got a big DC component here. That's because the DAC outputs the signal from 0 to 1 volt. So we're going to have half a volt of DC component there. But you can see we've got these harmonics as well. So we've got 2, 3, 4, 5, 6. So we have these harmonics, which are artifacts of the NCO, of the way that the NCO generates the sine wave. And curious to know whether this can be improved if we use the large ROM architecture to implement this NCO. So I'm going to go back, I'm going to recompile my design. I'm going to go into IP components and I'm going to go back into my NCO. It might make me close signal tap before it will give me the privilege of going into the NCO here. But if I go into this NCO, I can regenerate the NCO with the large ROM architecture, because remember, this is the Cordic architecture at the moment. So I'm just curious to know what the difference will be if we look at the large ROM architecture. So I'll be back in a second with the new design. So I've reopened the IP parameter editor. At the moment it's on Cordic, so I'm going to change it to large ROM. Now it does say here that the large ROM gives the greatest accuracy, so let's put that to the test. Now I do recall trying to use the large ROM architecture on the DE0 Nano board, and it just wouldn't work because it doesn't have the memory resources to pull it off. So there's going to be a significant increase in memory utilization with the large ROM architecture because it uses the lookup tables to generate the sine wave from the phase. As I said before, on the Cyclone V, it's not an issue, but I'm interested if we compare the Cordic, we can see those spurs at these frequencies. With the large ROM, everything is pushed down. So I just wonder if we can see that with the picoscope. Let's generate this. So the new design is compiling. We're about halfway through, and you can see the number of memory bits has gone up significantly. I think this was around 15,000 in the Cordic-based design. So you can see the price you pay for using the large ROM architecture is an incredible increase in the use of memory bits in a design. If you've got them, it's great. But if you haven't, I'm afraid you have to look for other options in terms of implementing the NCO. Okay, so this is the large ROM implementation, and it looks pretty similar, it has to be said. I'm not sure if this is because of the way the picoscope is recording this waveform, but it does look pretty similar. I'd have to look at these two waveforms pretty much on top of each other before we can make any conclusions about which one is better. But anyway, this one is the large ROM implementation. Now, before we finish, I just wanted to show you a kind of a trick that you can do with the numerically controlled oscillator. Now, this phase increment value, we know that the output frequency is proportionate to the value you put in here. So what I've done in this design, which is a modification of the design we've implemented in this video, what I've done is I've created a register called phase increment, and I'm incrementing the phase increment value on each positive edge of the clock. And what this will do is it will create a chirp waveform where the output frequency is increasing. This is something which is quite useful in some applications. One that springs to mind is the LoRa, the new LoRa communication standard, which uses a chirp waveform. So very simple to do. This is what the NCO, it gives you the flexibility to actually change the output frequency in real time. And again, another great application of this is just a signal generator. So it would be so simple to have a push button or some kind of input which changes this to whatever frequency you want it to be. So that's another kind of neat trick that you can do with the NCO. Now, I've already programmed the device, and you can see I've taken a snapshot of the chirp waveform. So you can see the frequency slowly increase, and then it gets to a point where it maxes out, and then it rolls back to the low frequency. So again, another interesting trick that you can do with the numerically controlled oscillator. So that's where I'll leave it for this one. I hope you enjoyed this video on the NCO mega function, and I hope you can incorporate this into your next project. So thank you for watching, and I'll see you in the next one. Bye for now.